Hello and welcome. You can see a problem at the screen, and I think it's better to read the statement of the problem first and try to understand it. So, the statement of the problem is a curved capillary of radius r filled with liquid rotates around a vertical axis A dash O dash. The picture is not quite clear, but you can still identify the points A dash and O dash in this figure. And at what angular velocity of rotation will the liquid begin to pour out of the capillary? From here, I guess. And the density of the liquid is rho, and the surface tension is sigma, and the liquid completely wets the capillary, and the dimensions of which are shown in the figure. So all of the properties of matter is in the same problem. We first try to learn this problem. The capillary rotates. This is the first thing. And the liquid begin to pour out. This event is going to happen at point B. There is no doubt about it. And surface tension, the role of surface tension is important here. And the next thing is the liquid completely wets the capillary. That means we are going to see some meniscus forming, and the shape of the meniscus should be hemispherical because this liquid completely wets the capillary. I guess here should be the pressure. This position, the pressure should be, inside pressure should be greater than the outside pressure for the liquid to pour out. So meniscus will take the shape in this form, and this inside pressure, I would like to call it PB. This must be greater than the outside pressure, PO. Outside pressure PO, I just named it PO. And this here will be in the shape also in the form of hemisphere. That means the radius of the hemisphere, radius of the meniscus is the radius of the capillary. That is equal to R. And we know this pressure, this is also the outside pressure, and this is the environment, so I would like to call it outside pressure. This must be greater than the pressure, this inside pressure, and we need to write equations for this. And on the basis of the concepts of surface tension and the hemispherical surfaces, we can write here PB minus PO, that is outside pressure, that must be equal to 2 sigma by R. Sigma is the coefficient of surface tension of the liquid. And what about here? You can always write PO minus PI should be also equal to 2 sigma by R. And the vertical elbow, where the shape is concave from outside, and here the shape is convex from outside at the lowest position, that is at point B. So I can write this, and I would like to take one more point here, that is A dash. Basically I would like to write pressure here at PA dash, just considering the capillary to be extra thin. And I can write one more thing. PA dash minus rho GH, that will be equal to PI. And if I can put these things, this equation, no sorry, this is equation number 2, this is our equation number 2, and this is 3. Then if we can merge equation number 3 into equation number 2, we are going to get something like P naught minus PA dash minus rho GH, and that will be equal to 2 sigma by R. That means P naught minus PA dash plus rho GH, that is equal to 2 sigma by R. That means P naught minus PA dash will be equal to 2 sigma by R minus rho GH. That means PA dash minus PO will become 2 sigma by R. Sign needs to be changed and it will become rho GH minus 2 sigma by R. And if I take the reference level as pressure outside, with respect to the pressure outside, I can write here PB equal to 2 sigma by R and PA dash equal to rho GH minus 2 sigma by R. And this is my final take for pressures, as far as pressures are concerned. And let's think that now rotation begins, and we have the shape like this here, and shape like this here, and this length is and it is rotating in this direction with an angular velocity omega, and omega is the speed at which liquid start to pour out of the capillary. If I can assume omega is the desired velocity. So to solve this problem, I'm going to, its length was perhaps L, this height was H, and its whole length was L. So I'm going to take the midpoint of the horizontal elbow of the capillary, which will be at a distance L by 2 from both ends. I am going to take two symmetric segments. One segment is this, and this is at a distance x from the center of the horizontal elbow, and another is also at the same distance from the midpoint, that is at a distance x. And what I did, I mentally divide the horizontal elbow into n segments, altogether L segments of very small length, and this length is what it is at distance x, so its length is, I consider its length is delta x, so will be its length, and delta x is nothing but total length L by n. N is the number of segments, and this delta x is of course very much less than L, so they can be treated as a point if you like to. If you don't, this length is delta x. Delta x is much smaller than L. So let us consider these two small capillaries containing liquid of mass. These two containers, capillaries, part of a small capillary. It is itself a small capillary. It contains a liquid of delta m equals density. Its density is rho multiplied by volume. This is its surface area, pi r square, multiplied by this thickness delta x. So they contain that much amount of water and located at same distances from the middle of the horizontal elbow. And we would like to write the equation of motion for these elements, these elementary part of elementary segments. And so the pressure difference here will be simply, I would like to call it P1, and this is P2, and this is P3 and P4. Yeah, I just named it arbitrarily. Yeah, P1, P3, P1, P3 are the pressures on these elements from the left, and P2 and P4 are the pressures on these elements from the right. And we can write the equations as P1 minus P2 will be equal to its mass m omega square x, that is m omega square, and its distance from the axis of rotation is simply L by 2 minus x. So I can write the equation of motion of this segment, and in the similar manner I can write for this segment, that will become P3 minus P4, that will be equal to delta m omega square L by 2 plus x. I just wrote those two equations to balance the centrifugal. That way you can consider that I am working in a rotating frame with respect to which the liquid in the capillary is at rest. So the force balance equation is this, and I'm now in the mood to add them. So there will be I know that number of such pairs of segments will be obviously n by 2, because total number is n, so number of such pairs is obviously n by 2. And if we can add for 2, and for all such pairs, I could write all such two symmetric pairs. I can write these two equations and add them. So I'm going to adding all the equations for all such segments, and I can write n by 2 delta m omega square L, because you can see here x gets cancelled out, and L by 2, so it's number I added n by 2, and that will be equal to the pressure PB minus PA, and since this is the force, I would also add the force here, pi r square. I made some mistakes. I should have written here, instead of P1 minus P2, I should have written here P2 minus P1. My mind was somewhere else, so this will be P2 minus P1, because the centrifugal force is acting outwards, and so this P2 minus P1 will balance the, and I have made a mistake writing not writing the area here. So I'm just making corrections in my writing, and now you can say this thing is very correct thing to write here after adding for all such pairs, and put all the values, and you will get, you can put for n. I already calculated n here. N, you can calculate n from here, and you can also write delta m from here, and just put all those things. You will get the result simply as rho omega square L square by 2 equal to 4 sigma by r minus rho gh. And now you can calculate the value of omega, and this omega you are definitely going to get as 8 sigma upon r minus 2 rho gh divided by rho L square, and the problem is solved. Thank you very much for watching.